The next section, chapter 25, 6, is about the electrics and Gauss law. So we're not done with Gauss law still. And in a capacitor with a dielectric, we will distinguish free charge from induced charge. And when a dielectric partially or fully fills the space in a capacitor, we'll find the free charge, the induced charge, and the electric field between the plates, and the potential between the plates. So some of these I'm gonna do it in the class, but I would like to go over briefly about on this slide. So how does this affect a capacitor? In part A, you see that it's just filled with air, so kappa is 1, and in part B, we can see there's a dielectric material. It's even has a bigger size than the plates, and we can also think about how does that affect the results. And so just like before we did use the Gauss law, we are going to, you can see that box, the pink box, and it says Gaussian surface. That's our Gaussian surface, okay? And if you also recall, the only part that really matters for us is the same area as the plate area, and it is between the plates, because inside the conductor electric field is 0. So on this surface there is no electric field, on the sides there is no electric field. Okay, so the only electric field is on that side, and you can see that E naught is from positive to negative on the surface that way you need to draw it, right? And then you can also think about the area. It's a outward, so that's the area direction. And again, you can use the flux equation, right? So in this case, again, we are enclosing that positive Q, and at the bottom we have negative Q. So when you have a dielectric material, as you can see it on part B, what really changes is those slightly polarized or induced charges. Okay, so these negatives on the top, we can see, and we call them negative Q prime, and the positives at the bottom of the dielectric material, and we call them positive Q prime. Of course, they're going to be the same magnitude. That's why they're Q prime, and they're going to be always less than that Q. So Q prime is always less than Q, because Q prime is there because it's induced by Q, but it's not going to be as much as Q, because the electric material is like insulating material, right? But it's not perfectly insulated. So in this case, if you compare E naught to E here, the E is going to be less, because the enclosed charge here in the first case is simply Q, but the enclosed charge here is Q minus Q prime, right? That's how much you're enclosing. So since Q enclosed goes down, and from the flux equation on the other side, with the electric field is going to go down when there's less enclosed charge, as we have less in part B. Okay, that's the reason the electric field reduces. So if you look at the Gauss law point of view, you will get the same answer. So first of all, capacitance is what? Again, kappa is 1 for now, right? But let's just put kappa here. Epsilon naught A over D. And so again, kappa for the first case is simply 1. Here it is not 1, okay, because not air or vacuum. And what we are seeing is we have like this kappa and epsilon naught are kind of together. So when you see epsilon naught, you're just putting kappa next to it, okay? So since before we used epsilon naught times A over D as the capacitance, so this kind of becomes C times K, or kappa times C, and that C is for the capacitance for air. So what you see is, again, these C's are not the same, just to give you an idea that capacitance increases because you have more K now, kappa now. And adding a material increases the capacitance. Okay, so that's what we observe. And for the same voltage, since Q is equal to CV, we know that V is the same, and we are saying that since it's the same voltage, capacitance increases. What happens to charge? Charge also increases. Okay, and if there's same charge, now the voltage is Q over C. We said that C goes up, and we are saying that charge is the same. You can see that voltage is gonna decrease. It decreases. And the energy also changes, but how it changes depends on what is constant and what is changing. So if you we know that the only thing I can say right now is capacitance is increasing, right? And you can see that if the voltage is the same, so you have this one the same, right? And then the energy will be increasing. Instead, if I have the charge the same, since capacitance is increasing, energy would go down. And that's why you need to check which one is constant. Whichever is constant, you're gonna pick that equation. So we have like two things related. You're just gonna choose the ones. If the problem says it's isolated, or Q is constant, then you're gonna choose the second one. If it says connected battery, then you know that same voltage, then you're gonna keep the first one to figure out the change in energy. And we are going to look into these in more detail after looking at a couple brief questions, and we will understand the concept better with some follow-up. You can see that here, follow-up questions. So we're going to solve a sample problem to understand quite a few things. There are several parts here. We're going to do that in class.